So each week in this module, I plan to do something I'm calling a toolkit. This is about energy basics, about calculations, problems, conversions, and efficiency, more working out problems, I suppose, than the concepts that are in most of the lectures. And this week we'll take you to some very basic energy concepts, energy units, and conversion of energy. This will be a revision of basic physics for many people, but for others it will be maybe a look into new concepts. So I suppose the first topic is, what is energy? And energy is actually notoriously difficult to define. Many different physicists and scientists have tried to define what energy is, but what the most commonly used expression is that energy is the capacity for doing some kind of work, something useful, something that we need from it. And there are different forms of energy. I'll go through this lecture the basic different forms of energy, especially that we'll be encountering in this module. So the most common form of energy is thermal energy, which is basically heat. This can be the heat of a substance, a liquid, a solid. And the measure of that is temperature. So obviously the higher the temperature, the more energy that's present in the form of heat. And the larger the body that contains the heat that is hot, the more heat there is, the more thermal energy there is. A second form of energy then is kinetic or mechanical energy. That's the application of a force over distance, and this is energy due to motion. The energy of movement, for example, the wind in the air or the water in the stream. And the faster the wind is, or faster the stream flows, the faster the roller coaster is, the more energy it can deliver. And that mechanical energy can also be called shaft power, and that's the energy in a rotating shaft, for example, a flywheel. For example, the power that makes the shaft rotate. Two more forms of energy that are very significant. First of all, it's chemical energy that is stored in food, in fuel, or in batteries. We encounter that very much in energy systems, and when we're thinking about sustainable energy, how much actual energy is stored in a litre of oil, or in a tree, or in a battery. This is very significant when we talk about energy units. So wood and oil contain energy in this chemical form. Anything that can burn basically contains chemical energy. And the metric for chemical energy is the calorific value of the material. And next week we will talk about the calorific value of different fuels. Chemical energy is also in a pizza, in in the bodies of animals, and so on. Fourth type of energy is potential energy. So, for example, water held in a reservoir at a certain height. The more water there is and the higher the level it has potential to fall, the greater potential energy there is. A fifth type is radiation energy. That's radiation from the sun. So all radiant energy is somewhere on this electromagnetic spectrum here. And also the radiation from light or fire is this type of energy. So more solar energy is available when the radiation is more intense, and also when it's collected over a larger area. And light is this visible part of radiation here. This is taking you as a whistle-stop tour through many different chemical and scientific disciplines, so I hope I'm doing them justice. A sixth type of energy that's very important for us is electrical energy. And indeed, when a lot of people think about energy systems, they only think about electricity, not all the forms of energy that are flowing through the energy system. So electrical energy comes from a dynamo or a generator, and they can deliver, so the higher the voltage and the higher the current, the more electrical energy that's available. Next is, what happens when we transform different types of these energy between one form and another, or what happens when energy is transformed, and are all these types of energy the same? In one sense they are all the same, or they are all equivalent. If you're familiar with the first law of thermodynamics, there's, energy can't be created or destroyed, just converted from one form to the other. So energy is conserved in any type of energy conversion. But also know, really all energy is not the same, in the sense that there are some useful forms of energy and some less useful forms of energy. And we measure this type of usefulness with entropy. So entropy is a measure of something, of the disorder of a system. So we can say the higher the entropy, the greater randomness or disorder or less use that the system is. So the more disordered something is, the higher the entropy. And the second law of thermodynamics states that typically systems get more disordered. So typically entropy tends to increase. We have a few examples here. So if you have the equivalence between a pile of bricks and different forms of energy, this nice pile of bricks here, which is made into a well-structured wall, it's useful, it's highly ordered, it'll create stability. This is a low entropy system, but over time it will tend to fall apart. So the entropy will always increase, the disorder always increases, so the wall always will tend to fall into a pile of bricks, which is completely useless. The same here example is for an ice cube. An ice cube is a crystal structure. It has low entropy and high order, but over time it will turn into a puddle, and the entropy will be increased. And similarly, if we have an original solution and a dye, these are two more ordered systems. If you add the dye to the solution, it diffuses and becomes less useful, so you can't extract the dye back easily out of the solution. What does that have to do with energy? Well, we can distinguish between different grades of energy. So some forms of these energy are useful: electrical, chemical, mechanical, nuclear energy. They're all useful forms that we can put to different tasks that we need. Thermal energy, for example, in a bath of water, is less useful. So you can use electrical energy to run your TV, or you can also use electrical energy to convert it into heat to boil a kettle, for example. But you can't do either of those things with a tepid bath full of water. You can't run an electric vehicle with a bath full of water, even if the bath might contain an awful lot of heat energy. It's not very useful for the energy system. And we can distinguish between different grades of energy in different units. We can say, for example, a kilowatt hour E is electrical energy, and a kilowatt TH is thermal energy, so different units. And the second law of thermodynamics also says that because entropy tends to increase, that means that when you convert energy from one form to the other, you'll typically lose energy, and that loss is usually in thermal energy. No energy conversion is 100% efficient. So when you burn chemical energy, for example, oil, to produce electrical energy, that's about 40% efficient depending on the system. So 60% of that heat that energy that was in the original oil is lost as heat, and about 40% is captured as electricity. Similarly, a steam turbine needs a low temperature to dump entropy, so it needs, you need a place to dump that heat, if you're good more efficient. And if we use the example here as well of the food chain, here's the food chain. So it all starts with sunlight. So if 1000 joules of light energy from the sun as radiation falls upon a plant, that system of photosynthesis creates chemical energy in the plant. Only 10 joules of energy are available as food. So that conversion is only about 1%. These are all orders of magnitude, not exact numbers, but about 1% efficiency that photosynthesis system is. So 990 joules of energy are lost to the environment as heat. Actually, photosynthesis produces a heat reaction. So if those 10 joules of energy in that plant are eaten by a herbivore, so an animal that eats only plants, 9 joules are lost to the environment, and 1 joule is available as food energy to a carnivore. So this conversion between the chemical energy in plants to the basically the body of a herbivore, is about 1% efficient. And similarly here, if 1 joule of energy can be captured by the lion, 0.9 joules are lost to the environment, and 0.1 is available. So again, this conversion is 1% efficient. So if you multiply 1% efficiency here by 1% efficiency by, this is 10% efficient. So 10% efficient by 10% efficient by 1% efficient. That means you have to multiply all those efficiencies together. The food chain is about 0.01% efficient. So about 0.01% of this energy from the sun gets into the lion in the end. That shows you how much energy is lost to the system. And it also shows you how much more it makes sense to, in energy conversion terms anyway, to eat plants than it is to eat carnivores. If you think about an example of an energy conversion of decreasing entropy, that's an interesting one. So typically, you know, if you think about different energy conversions, most of them will decrease entropy. So if I use electricity to boil a kettle, I get heat. That heat dissipates over time. It's not that useful, although cups of tea are very useful. But one nice example of a system of an energy conversion process which increases the energy grade is here from sunlight to plant matter to chemical energy. That's photosynthesis, and that's, I suppose, the basis of all life on Earth, and that's a particular system. Here is an example of a very simple electrical system. So this is a steam generator that converts oil or coal or gas or whatever to electricity. In this generator, the high grade energy dumps the thermal losses into this coal store, and then produces electricity into towns. And as I said, that system is about 40% efficient, depending on the system. These are some different conversions in the energy system. Usually we start with chemical energy. All fossil fuels are stored as chemical energy, and biomass is also stored as energy. Here, for example, that pizza. So you can convert that oil, gas, coal into electrical energy, or you can convert it into kinetic energy in a car, or that electrical energy can go into a car through a battery. You can convert it to mechanical energy. For example, in a spacecraft, that electricity then can be converted into light or to sound and light. And similarly here, chemical energy can be converted into work in the body. You don't need to remember all of these, but here are examples of different energy conversions. So if you're going from, say, chemical energy into thermal energy, this is one of the main forms of energy conversion in the energy system, and that's called combustion. So when we convert from chemical energy to thermal energy, it's combustion. We can also go from, let's say, picking some of these, thermal energy back to thermal energy. So you can go from low-grade heat in the environment to high-grade heat, and that means low-temperature heat to higher temperature heat with a heat pump, which I've already mentioned, and that's with a heat exchanger. Here are, for example, from kinetic energy here to gravitational energy. You can rise things up and create energy like that. Okay, now we go into the units of energy, and to go back to the units of energy, I introduce you to the International System of Units, or you might already be very familiar with that. These are 7 basic constant units in the universe that have been agreed by scientists. That's the standard SI unit of length is the meter. The symbol is M, and also the capitalization here matters. So don't use a capital M for a meter. A kilogram is the standard unit of weight. Mass. Second is the standard unit of time. Ampere of electrical current. Kelvin is K. The mole is the amount of the substance, mole, and luminous intensity is the candela. So we will typically only deal with the first few of them. And the interesting thing about these is that as of last year, they have all been defined in terms of universal constants rather than some physical entity on the planet. So previously there was, a kilo of, I don't know what it was, something very non-reactive in Paris, and there was a meter stick. But now they're all defined in terms of the speed of light and different universal constants like that. These are the standard, the SI units for multiples, and you'll need to know these for this module. You'll need to know these particular ones for this module because you might be asked what a petajoule is, or that's 10 to the 15. That's quite on the outskirts of things, but these come up an awful lot in energy units, because if you're talking about, you can talk about the kind of local scale or the global scale, and the units of energy come change an awful lot. So it's worth generally in your life remembering these, and my little mantra is kilo, mega, giga, tera, peta. So a kilo is a million, is 1,000 at 10 to the power of 3, mega is a million, 10 to the 6, giga is a billion, 10 to the 9, tera is a trillion, 10 to the 12, and peta is a 1,000 trillion, 10 to the 15. Peta doesn't come up very often, but kilo, mega, giga, tera, peta. That will help you. They're all capitalized except for kilo, for K, and just remember that capitalization again. Submultiples then we don't typically use, maybe the milli, 10 to the minus 3, so 1,000th of a something, but I thought I'd include that as well. So the most important derived SI units, so in science we derive most units from these SI units, and these are the important units for energy. So force is the acceleration of a mass of 1 kilogram by 1 meter per second each second. So that's a kilogram meter per second, which is second squared. Kilogram. So, and then energy, so that's called a Newton, and the symbol is N. The standard unit for energy is the joule, and that's the most important thing in this lecture. So the symbol is a J, and the unit is a kilogram meter squared per second squared. So that's an extra meter. So basically it's the force of 1 Newton acting over 1 meter. And thirdly, the unit of power is a watt, and the symbol is the watt, is the W, and that is the energy flow per unit time. So it's a joule per second, or a kilogram meter squared per second cubed. So energy flow per unit of time. And the difference between energy and power is something that comes up very often. If you can compare it to, let's say, measuring water, you say the energy would be like the volume of water in a basin or something. It's the amount. It doesn't there's no time dimension to it. There's just a particular quantity of energy, and the and the power is the equivalent of the flow of water per unit of time. So how quickly, say, a tap how quickly water is flowing from a tap. So this reinforces that fact. So converting energy to power, energy is power multiplied by time. So 1 joule equals 1 watt a second. You'll be familiar with different light bulbs. Typically now they're more like 5 watts in LED lights, but older light bulbs could be, for example, 40 watts, 100 watts. And that means it's consuming 40 joules of electric energy per second. That is what a 40 watt light bulb consumes. Or when it comes to solar, 250 watt solar panel produces 250 joules of electric energy per second. We'll go through a few of the non-SI units for energy, and then I take you through calculating some calculations, converting forms of energy. So much like there's the kilometer and a mile, or an inch and a centimeter, there are different non-standard units for energy which come up time and time again because different organizations use different units, or they're useful for different things. But it's very important to understand these things. So the British thermal unit, or the BTU, is 1055 joules. That's the equivalent of 1055 joules. This is a traditional measure of heat, obviously developed by the British, and that's the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And you can see the older imperial system in play there. A calorie then, most of you will be familiar with what a calorie is. So the calorie is the heat needed to raise temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius under standard pressure conditions. And the amount of energy in terms of joules, 1 calorie is 4.18 joules. So that's the amount of the number of joules needed to raise 1 gram of water from 14.5 to 15.5 degrees Celsius. And an adult diet needs around 2,000 kilocalories. What we call calories in terms of 200 calories in a chocolate bar is actually a kilocalorie. A third unit, which is very important, is called the kilowatt hour. And this is the standard unit on your electricity meter. So you will say consume 100 units over a period. That is actually 100 kilowatt hours. And it's very important to understand that. So that's the power of 1,000 watts. Kilo, 1,000 watts in 1 hour. So if you've got an electrical appliance that is consuming 1,000 watts, and you have it on for 1 hour, then you'll consume 1 kilowatt hour, and we can convert that into joules. I'll do that in a second. And we can also define units of energy in terms of physical units. So that's in terms of a physical unit is like a ton of coal or a liter of oil. And some of the common ones here are ton of oil equivalent, TOE, and many different systems you'll see is KTOE, so kilotons of oil equivalent, and the Irish energy balance, so the energy statistics are typically in terms of KTOE, kilotons of oil equivalent. So we convert all the different forms of energy flowing through the energy system into the equivalent weight of oil, 1 standard ton of oil. And it's defined as a ton of oil having a net calorific value of around 42 kilojoules per kilogram. There's also systems which convert things to tons of coal, standard tons of coal, or volumes of natural gas, typically meters cubed. So here I will go into what the equivalence between the kilowatt hour and the joule. So 1 kilowatt hour, it's a unit that we see an awful lot, and it's a very confusing unit because actually a kilowatt hour is a unit of energy, and energy doesn't have a time dimension. It's in this way. So a kilowatt hour can be spread over a day, a second, and so on. So the hour unit in there is quite confusing. I hope this helps to clarify. So we can convert this into megajoules by saying 1 kilowatt hour is, kilo is 1,000, so 10 to the power of 3. A watt is a joule per second, so times joule per second, and an hour, so we want to convert the hour into seconds there. How many seconds are in an hour? 60 times 60, so equals 3,600, which is 3.6 by 10 to the power of 3 seconds. So we can cancel off the seconds, so it equals 10 to the 3 times 10 to the 3 is 10 to the 6. Times 3.6 joules. So that's 10 to the 6 is a million, so mega, so equals 3.6 megajoules. So that's a simple conversion from a kilowatt hour to a megajoule.